Hi, everyone. My name is Tainara Borges. I'm going to start by introducing myself. I am a graduate student at Brown University. My advisor is Professor Pipher. And today I want to talk a little bit about bilinear averaging operators and singular variants of the Falconer distance problem. Before we get into that, though, let me also mention what are the things that I've been interested in so far. I like harmonic analysis and geometric measure theory questions. I'm very interested in the interplay between the Fourier transform and the geometry in Hausdorff dimensional sets. And for my PhD thesis, I've studied some bounds for bilinear averaging operators and associated maximal functions. Such bounds include Sobolev smoothing estimates, Lebesgue bounds, some sparse domination estimates, and so on. I've looked for connections between bilinear averaging operator information and questions in geometric measure theory, which we're going to talk a little bit about later. And I've also looked into commutators for hardships in the context of leveling measures. Let's get started with the map though. So it's there's an object that's going to be important in this talk, and that is the spherical average of F around the point X with radius T. What does it do? Imagine you are in dimension at least 2. You have a point X, it's going to be the center. Look at a sphere of radius T around the point. If you have a nice enough function, say Schwartz, you can average the function in that sphere. This is going to be the operator ATFX. Once you have those averages defined, you can look at a maximal function associated to it that captures what is the worst and what is the largest that a spherical average can be around the point X. By doing that, you get the spherical maximal function, and the boundedness properties in LP of this operator are well understood. It's known that it maps LP into LP as long as you have P larger than D over D minus 1. This is a theorem by Stein when D is at least 3, and later Bourgain also showed that is true for D equals 2, which was a little harder because you don't even have boundedness in L2 in that case. And there are like multiple reasons why you could care about spherical averages. If you're a PD person, for example, the ATFX quantity could show up as solutions of certain PDEs. And this maximal function could give you information about like almost everywhere convergence results when time goes to 0, for example. There's also like packing of spheres and other questions, but the reason that we want to explore today is there's also connections of bounds for spherical averages and a question geometric measure theory. This is the Falconer distance problem. So I'm going to start by defining what the distance set of E is. So let's set this up. You are in dimension at least 2. You take your compact set E in RD. The distance set of V should capture all of the distances that are attained by pairs of points in E. This notion of distance here is just using the usual Euclidean distance in this setting that we're looking at. A natural question or an interesting question is how large do you have to make the dimension of V so that you can guarantee that there is a lot of distances in the distance set? And the notion of how large is often like the notion of Hausdorff dimension. How large do you have to make the Hausdorff dimension of V so that you guarantee that delta E has lots of distances? To make this conjecture precise, so Falconer conjecture from 85 says that if you have a compact set in RD, be at least 2, and the set has mentioned at least half of the ambient dimension, so at least over 2, you should expect there is a lot of distances in delta E in the sense that that is a positive Lebesgue measure set. This Falconer conjecture, the way you stated, is actually an open question in all dimensions, and it doesn't even make sense if you're in dimension 1. But people have gotten very close to D over 2 by giving a little bit of room. And the Falconer distance problem has a very huge history, very interesting history. So Falconer at first showed that you could do it with d over 2 plus an extra half. As long as the dimension of v is larger than that, you could guarantee positive Lebesgue measure for the distance set. That extra half was being dropped throughout the year. So in 99, Wolf, and then in 2005, Erdogan, they dropped the 1/2 to 1/3. Then the one Zhang in 2019 dropped that to 1/4 plus 1 over 18 is 4. So pay attention to the magenta numbers. You see them dropping. Then after that, in dimension 2, Goof, Iosevich, Owen, and Long showed that it's enough to ask for dimension larger than 1 plus a quarter. And that was extended for even dimensions by Du, Iosevich, O, Wang, and Zhang. And last year, there was also a very nice improvement in the threshold for every D3 that actually asked this extra amount in magenta to be 1/4 minus a small number. So this is the first time that you actually ask less than a quarter here. Going back to the spherical averages, you could think of this operator in the Fourier side, and you're going to see that it's a multiplier operator, and the symbol is sigma hat of TXC. One very nice thing about the Fourier transform of the spherical measure is that it has very nice decay of the form 1 plus c to a negative power. This negative power is minus d minus 1 over 2. It has to be with how many non-vanishing curvatures the sphere has. If you just use the decay estimate for this for the Fourier multiplier, you're going to see that when you're mapping L2 into L2, you actually gain d minus 1 over 2 derivatives. And you can state that by saying that for every t, for every fixed t positive, your operator AT maps L2 in this H d minus 1 over 2 Sobolev space. So here I'm calling the notion of the inhomogeneous Sobolev space. If you use this information about the decay of the Fourier multiplier, the Sobolev smoothing, and L2, you can get a lot of information about the distance set. We're not going to dive into this right now, but it is the case that the Fourier transform of sigma, just by having this decay, already gives you some nice information about the distance set of V. Let's move to a bilinear setting now. Imagine we want to now have two input functions spill out in average around point x, and it's going to be defined in the following way. You take your two functions and define where you want to average x, your radius t, and you take an integral in the unit sphere in R2D now. Okay? You look at the definition of the bilinear spherical average, and you're like, why are you doing this, right? The pair YZ lives in the unit sphere. There. I like to rewrite this in the following way sometimes because it becomes a little bit more clear what is happening. If you were to average the tensor function around the point XX in R2D with a radius t, you would actually end up with the bilinear spherical average. So all that this ATFGX is a average around the diagonal point XX for a tensor function, but now the ambient space would be RD cross RD instead. Okay, so keep this picture in mind for the rest of this talk. We could also think of how does this behave in the Fourier side in the same way that we did for spherical averages before. If you're writing this as a bilinear multiplier, this thing in red is what the bilinear multiplier would be, right? So this equality is true. It's not a very hard computation. And again, we do know what is the decay properties, what are the decay properties of this symbol in red, by the same reason that we had decay properties for sigma hat before. So sigma hat in all its derivatives decay like a negative power of c eta, and this negative power is 2d minus 1 over 2. Okay? Because the decay doesn't get better with the order of the derivative, there is oftentimes this kind of multiplier is called bilinear multiplier of limited decay. So this decay in blue is not changing with alpha, which is the multi-index for the derivative. There is geometric information that we can get for bilinear spherical averages. So let's define this box E set. You start with your compact set in RD, and then you define box E to be all distances from diagonal points of E cross Z to non-diagonal points of E cross Z. So what you see in red right here is a point of the form XX. So this is going to leave in the diagonal of E cross Z. What you see in blue is a point that is outside of the diagonal. If you collect all of those, you're going to end up with a distance set that is singular in the sense that we're taking distances from sets that have different dimensions. So the diagonal of E cross E is much lower dimension than the set E cross E itself. That's why we call it a singular Falconer distance set. This picture I borrowed from another paper that also studied this box E set with a slightly different strategy. It's a paper by Gaitan, Greenleaf, Paulson, and Sadonides. Let me tell you what we know for box E. Okay? So if you just use Sobolev smoothing estimates for bilinear averages, you can already get some information for box. So we showed with Iosevich and all in 2023 that you can get positive Lebesgue measure for box E. If the dimension is larger, dimension of V is larger than D over 2 plus a quarter. And this works for every D at least one. Gaitan, Greenleaf, Paulson, and Sadonides, they looked at the question of having an empty interior, and they got that the dimension of V larger than 2D plus 1 over 3. So you see this is larger. Right? Actually, both of those bounds, if you are in dimensional case, sure, there is a better way of doing this. We exploited that in the same paper with Iosevich and O by showing that if you have a threshold for the Falconer distance problem, you can actually transfer that threshold to the box E set and get a non-empty interior result. So the best threshold would be the same as the thresholds for the Falconer distance problem as long as you are in dimension at least 2. In dimension 1, the D over 2 plus a quarter is still the best we could do. Now let's move to some maximal functions, right? It's in the same way that when we're talking about linear averages, we could take the largest possible average along the point. We could do the same here now that we have this notion of a bilinear spherical average. This is going to produce a maximum function that we're going to call the bilinear spherical maximum function. The place where this maximum function first appeared was in this paper by Giba, Greenleaf, Iosevich, Paulson, and Sawyer in 2013, which hasn't been that long. And at first, people were interested in getting to know what are all the Lebesgue bounds properties for this bilinear spherical maximum function. You could think that you're trying to map LP cross LQ into LR, and you're starting with P and Q that live in the Banach range between 1 and infinity, but you're going to be taken oftentimes outside of the Banach range. So the R here becomes smaller than 1 for certain choices of P and Q, and you want to know the sharp range of exponents for which you can have this map bounded. After efforts of many authors, Zhang and Li, after finally figured out what the sharp region should be, they showed that it's the following. So first of all, people already knew that for this operator, the only chance of having a bound is if the exponents PQR satisfy a Hodge relation. And by Hodge relation, I mean 1 over R has to be the sum of the inverse of P and Q, what you just see right here. And we can present this in a picture at first, like just plugging the 1 over P and 1 over Q. If we had no restriction in R, you could think that we would get the full unit square. But Zhang and Li showed that the sharp region requires R larger than D over 2D minus 1. Right? The fact that this condition was necessary was actually known, but they also shows that it was sufficient. So closing the question what the sharp region should be, and it's this picture that you see right here. You lose this triangle in the corner of the unit square. There is a variant of this function that is when you don't look at all possible radii around the plane X, but you restrict yourself to dyadic radii, and one should expect better boundedness properties for this function, right? But the methods in generally couldn't really capture um, restricted scales for the supremum because of their slicing strategy. So we had to investigate this in a different way. This is a joint work Ben Foster. We show that at least if you are in the dimension of at least two, you get basically the full square for the bounds of the Lacunary bilinear spherical maximum function, except for some pieces of the boundary where we still don't know if the boundedness fails or not. So the dashed red region here is just some open region as of now, but this gives the sharp region up to boundary. And you see those pictures are different. The one for the full range of radii is worse than the one for the Lacunary case, right? Understandably, this operator is small. And you could even ask, okay, but you also have d equals 1 as a possibility for this averages, right? If you go back to the definition of the bilinear spherical average, that would be a situation where you would be integrating in S1. So you'd be integrating circles. In the case d equals 1, there is like different sets of authors that had investigated the question of the bounds. Chris and Zoe showed that you have the interior of the unit square, basically, as bounds for the Lacunary operator. They used trilinear smoothing estimates, which is stronger tool than the ones that we had to use. We tried to simplify the arguments for dimension at least two. When it comes to the supremum over all positive t, the bilinear spherical maximum function in d equals 1, the feature changes radically from the one that we had from German Lee, and you only get this square of silent 1/2 around the forming the origin. This was done by Kristen Zoe and Citizen almost independently, but with proofs and in spirit use similar ideas. Now I want to tell you something about more general averaging operators. There is no reason for us to restrict ourselves to the sphere, the unit sphere, right? We could take a compactly supported finite report measure sigma. It's going to have a certain support. We could define a spherical average around x of radius t the same way as before, just replacing the measure with this new measure. And there, imagine you take the associated maximal function to this notion of spherical average. So this would be the supremum of all t's, words that you could have around the point x. We will differentiate show that if you know some decay for sigma hat, right? So suppose you know sigma hat decays like c to the minus a, and this decay is large enough, larger than a half, then you can get a region of LP boundedness for the operator. And this region of LP boundedness was P larger than 1 plus 1 over 2A. If you think about it, what it's saying to us is that the best the decay of the sigma hat is, the better the boundedness properties would be, the better the range of LP bounds is. And in the particular case of the sphere, where this A should be D minus 1 over 2, you can actually recover Stein's result. You can't quite recover Bougrand's result just because the condition A larger than half fails. In that case, D equals to A is exactly half. Okay? But this puts things in a more general setup where all you're asking for is for the decay of the sigma hat. You could also allow more general dilation sets, right? So if instead of supremum, you take supremum over all radii, you take supremum over dilations of a certain fixed set of 1, 2, you're gonna have a maximal function associated to this dilation set E. How does this work? So if you think about what we're doing here, we're saying we do supremum for T and E and L and Z of spherical average with radii 2 LT. For every L, we're just looking at the relation of V. So this picture right here in the bottom is just illustrating this. Like you could have your set E to be this orange thing. And then when you scale by 2, you're going to have a new set between 2 and 4. When you scale by a half, you're going to have a new set between 1/2 and 1. And what that maximal function would be doing in this case is just allowing averages that sit within one of those dilations. In the extreme cases where you take E to be the whole interval, you would recover every possible radii, positive radii, and when you take E to be just 1, you would get the Latourneri case. So this more general setting captures things between the Latourneri and full supreme. But if you want to prove bounds for this more general setting, you would have to quantify how large the set of scale is, and you would need this notion of upper Minkowski dimension. So how does this work? Often what we do is we just think if you have a subset of 1, 2, you could check how many intervals of psi delta you need to go over E, and you call that in E delta. So this is how many intervals of psi delta you need to go over E. This dimension, the Minkowski dimension of E, the upper Minkowski dimension of E, should be the smallest beta that can make the following equality true. So you're saying if you're checking how many intervals of psi delta you need to go over E, you need something like delta 2 minus beta with some epsilon ones. Looking at the extreme cases, so if you're thinking of the interval 1, 2, you need 1 over delta interval, so your beta should be like 1. In the other extreme, when you just have 1 point, you really don't need any positive power betas. You could just take beta equals 0 and this is going to work. For a 1/3 counterset, you get something in between, like log 2 base 3. And there is subsets of 1, 2 that can realize any given dimensions. You can achieve things like 1 over 1 plus A for any positive A with certain sequences within 1, 2, for example. Now I will show you the following. So if you were to now ask for what are the LP boundedness properties of the maximal function that has general sigma and general dilation set E, Domenico and Vargas investigated this, which would be a generalization of Ribble-Frankfurter result, where we allow the more general set of scales. And they show that if you have the same decay as before, decay C to the minus A, and the A compensates half of the Minkowski, the upper Minkowski dimension of V, then you're gonna have bounds in LP with the associated maximal function as long as P is larger than 1 plus beta over 2. What this is saying at the end of the day as well is that this range of bounds gets better if you have more decay for the sigma hat, and if you have smaller dimension for your set of dilation scales. And this quantifies how good the range of LP bounds is. We wanted to investigate something like that in the bilinear setting. So the setup in the bilinear setting would be very similar. You still have a bilinear multiplier, but now you have a bilinear multiplier, and you're assuming that it decays with a certain negative power of C8. Then you take your bilinear spherical averages, just replacing the spherical measuring as 2D minus 1 with a more general finally compactly supported measure now in more 2D. In the same way as before, you can define this maximal function with intermediate set of dilation scales by dilating a certain subset of 1, 2. You're just going to have to use the right notion of bilinear average, right? In the extremes, you would have the Latourneri and the full range of scales case. Okay? Together with Foster and we were investigating all we can say as, about LP bounds for this maximal function. So we found that if you have a subset of 1, 2 with upper Minkowski dimension beta, and sigma is a finite Borel measure in R2D that has decay like minus A on the Fourier side, as long as this decay compensates half of the Minkowski dimension plus D over 2, you can get LP bounds that are of older type within a certain region. So what are we trying to say with this picture? We're saying you can guarantee at least that if you're trying to map LP cross LQ into LR and they satisfy the order relation, you could, it's true that that is going to be bounded if 1 over P, 1 over Q live in this red region. In particular, you could see that this recovers like bounds of the type 2, 2, 1, for example. Okay, that would be the point half, half here. When you compare, let's actually think of some particular cases, right? So look at this point that I mentioned right now, the 1 half, 1 half. This is implying that as long as A is larger than the quantity, you have boundedness in L2 plus L2 into L1. And let's think of a particular case for sigma. So imagine you have a surface. It's like 2D minus 1 dimensional compact surface in our 2D. Sorry, this should be 2D minus 1. Imagine you have a 2D minus 1 dimensional compact surface in your 2D, and you have a certain number of non-vanishing principal curvatures, say K. You put in this surface a smooth measure, sigma K, and you can define dissociated maximum function, right? So the one that would look at the averages around the point X with radius T. For all T's, you take sum of all T's. This operator was known to be bounded from L2 plus L2 into L1 as long as the number of unmentioned curvatures was larger than D plus 3. This is a paper by Chan, Faculty and Concept in 2022. Now, from the theorem that I just stated for you, you could actually recover this with a weaker condition that the number of non-vanishing curvatures, the number of non-vanishing principal curvatures is at least D plus 2. When you look at the case where you have dimension for a strictly smaller than 1, you actually just need to require K larger than D plus 1. And in the particular case where you're looking at a lacunary case, this was known by the faculty who saying John Park. Right? So this is recovering the result, but it's also saying it doesn't matter. You could actually replace the lacunary one with anything that has E with dimensions strictly smaller than. How do we do this? Like, if you just like one of the key ingredients to get to this region was the understanding of the Sobolev smoothing estimates for certain operators, the exponent 2 to 2. Let's dive into this a little bit. When you think of things in the single scale, you would take just the supremum over T in E. So E is a subset of 1, 2. All the parameters for the radii are things comparable to 1. That's why we're going to call this a single scale maximal function. And this operator has certain Sobolev smoothing properties. Okay? In the same setup as that theorem, right? You have certain dimension for the set of dilation scales. You have a certain decay for sigma hat of order minus A. And A compensates beta over 2 plus D over 2. Then we have some Sobolev smoothing of the following form. You not only map L2 plus L2 into L2, but you map this negative Sobolev spaces H minus S1 plus H minus S2 into L2, as long as S1 plus S2 is smaller than A minus D plus beta over 2. Intuitively, what we're saying is that when you map L2 plus L2 into L2, you gain A minus D plus beta over 2 derivatives. Right? Like one thing particular from the Bilinear case is that you have this extra D over 2 in the condition with comparison. If you compare this with the linear case, you do not see that at all over 2. And I think that's actually all I want to say. So thank you so much. Thank you. Also happy for giving the opportunity for me to speak in here. Very glad. Bye-bye.